Assalamualaikum warahmatullahi wabarakatuh. My name is Jasir bin Sulaiman. I'm from semester 7 from Faculty of Mechanical Engineering. I am being supervised by Dr. Baljit Singh and my FYP title is Solar Concentrator Power Generation using Thermoelectric Generator. Okay, first thing first, project summary. Solar Thermoelectric Generator, STEG, which is S stand for solar and TEG stand for Thermoelectric Generator. STEG are solid-state heat engines that can generate electricity using concentrated sunlight and the temperature gradient between the cool side and hot side of the TEG. In this proposal, I have compared the water-cooled and coolant-cooled, which is ethylene glycol cooling methods for the STEG. The solar concentrator used for the STEG model is the parabolic dish. The outcome of the theoretical calculation reveals the maximum power and voltage output across the circuit. For future advancements, it will depend on the system's capacity to produce the highest temperature gradient. We move on to the project background. The world's energy needs are dramatically rising as a result of population growth and industrial development. It is significant to highlight that developing nations have significantly contributed to the population growth, which has expanded by 2 billion people in just one generation. As a result, the demand for energy is rising quickly to keep up with global population growth. Additionally, if the world continues reliance on non-renewable energy resources, it has the potential to cause climate change, which in turn could result in severe natural disasters that harm the planet's ecosystems. One of the better possibilities is solar energy because it is a clean, renewable energy source and is widely available. One of the reasons that makes solar better than other renewable energy source, which is abundant. It is limitless. In harnessing solar energy, there is several technologies that have been successfully used in the past, which is concentrated solar power plant, photovoltaic, and the latest one is solar thermoelectric technology, STEG. STEG is a unique technology because compared to others, it has no moving parts. In this literature review, I have highlighted 4 points. So the first one is why solar energy? Because it is a potential source of energy in the world since it is non-exhaustible and provides solid and rising output efficiency compared to other energy resources. Study revealed that global energy demand can be fulfilled by using solar energy as it is abundant and required no cost. Solar systems can be utilized efficiently for village systems, industrial operations, and residential use because they are readily inexpensive and adaptable. So, for my next point is concentrated solar power, CSP. Okay, so these technologies use mirrors to reflect sunlight to a receiver, which then allows heat to be collected by a thermal energy carrier in primary circuit. This heat is then either used directly, in this case water or steam, or indirectly via a secondary circuit to power a turbine, which in turn generates electricity. The solar power tower and the parabolic trough collector are the two most well-known technologies that are used in concentrated power plant. These technologies have been demonstrated to be the most successful commercial solar thermal technology, with the ability to achieve a peak plant efficiency of approximately 20%. Okay, moving on to my third point, photovoltaic. The photovoltaic solar energy PV is one of the most growing industries all over the world. Due to photovoltaic effect, solar radiation is converted into electricity. Photovoltaic effect is a process that generates voltage or electric current in a photovoltaic cell when it is exposed to sunlight. This effect was first identified by Becquerel in 1839. This effect happens in materials known as semiconductors, which have two energy bands, one of which allows the existence of electrons and the other of which does not. Photovoltaic technology does not contribute to the major environmental issues that conventional power generating sources, including those employing fossil fuels, cause during generation, such as climate change, global warming, air pollution, acid rain, and so on. The downside of PV is when compared to nuclear technology, photovoltaic technologies use 64 times more material resources, 7 times more labor, and 10 times more capital per unit of power produced. So, for the last point in my literature review, STEG. Solar thermoelectric generator relies on seeback effect, which is using the thermoelectric technology. Seebeck effect, that is, when a temperature differential is formed across a thermoelectric device and a properly connected external load, a direct current DC voltage arises in the thermoelectric elements and an electrical current flow through the load. So a STEG can be broken down into five subsystems. First, optical concentration. So in my FYP project, I use the parabolic dish. It can be others. Second, thermal absorber. Third, thermoelectric module, which is the TEG. And the fourth, cooling system, which is the proposal for my FYP. And the last one is optional, vacuum encapsulation. So the things for STEG, when compared to other solar technologies, STEGs have a number of benefits that make them superior. STEG are solid-state devices as opposed to the classic solar thermal generators, which means they do not have any moving parts, which significantly boosts their dependability and durability. In addition, STEG are a scalable technology that may be applied on either a small or a large scale, depending on the requirements of the applications. STEGs employ a wider amount of the solar spectrum in comparison to photovoltaic, which are restricted to only using the portion of incident solar radiation that is above the band gap. STEG system efficiency depends on the optical and thermal efficiency of the collector, the ZT value of the thermoelectric modules, and the efficiency of the cooling method. Next, problem statement and objective. STEG has been gradually improved in order to better compete with competing technologies. In terms of efficiency, the technology behind STEG is not yet on par with CSP and PV. On the other hand, a substantial amount of research has been carried out in an effort to improve the effectiveness of the system. The problem with concentrated solar power is that it is implemented on a massive scale and necessitates a large deal of space. Photovoltaic, on the other hand, are not very cost effective because the construction process demands a tremendous deal of resources. Solid-state heat engines, also known as STEG, are superior than CSP systems in that they are able to operate at higher temperatures and do not call for any moving parts or operating fluid. So, the objective of this project are to analyze the efficiency of solar thermoelectric generator and to analyze the potential thermal energy and electrical output from STEG. Next, scope and limitation of the project. The aim of this project is to evaluate the solar energy harnessing technology. There is a variety of technology that have been used in the world right now, which is CSP, PV, and STEG. This study will solely cover about STEG, and that will be the design and efficiency of the technology. It will not involve the environmental factors, cost factors, and installation factors. The main parameter that will be focused of this project is optical observer and thermoelectric subsystem efficiency. So here is the methodology of my project. First thing first, I started with literature review by reading a lot of articles that related to solar technology on the web, such as Google Scholar and Sci-Hub. Next, I determined the objective and problem statement. So for the next session, it divided into two parts. So for this semester, I will just do the theoretical calculation for two different cooling methods that I mentioned earlier, which is the water-cooled and ethylene glycol-cooled for STEG system. For this calculation, I need to start off by input the cold side value of the thermoelectric generator. Then I can calculate the temperature receiver, temperature gradient, voltage, current, and the power output. After that, I need to compare both theoretical and experimental results. If the result is identical, I will proceed with the thesis writing. If not, then I need to start again with the experiment. Last but not least, expected result. So this is the result for my theoretical calculation. This graph shows the maximum power output and voltage across the load for two distinct cooling systems. The temperature gradient of water-cooled method is 149.122 Celsius, whereas the ethylene glycol-cooled method is 175.822 Celsius. The result indicates that as the temperature gradient increases, so does the system's power output. So this is the Gantt chart that shows the progress of my FYP throughout this semester. Thanks for watching and bye.